What if the key to a theory of everything isn't some undiscovered new particle, but empty space itself? We're about to dive into a radical new idea that tries to unify the entire cosmos by completely rethinking what the vacuum of space actually is. So get this. What if the biggest things in cosmology, dark matter, dark energy, even the idea of cosmic inflation, aren't real? What if they're just placeholders, patches we've put on our theories because we've been missing a much deeper, more fundamental truth all along? That's the huge question we're tackling in this explainer. What if we've been looking at the universe completely wrong? Now, to see why anyone would even propose such a wild idea, you have to look at the cracks in our current picture of the universe. First off, our standard model says a whopping 95% of the cosmos is made of dark matter and dark energy, which is really just a fancy way of saying we have no idea what 95% of everything is. Then there's the Hubble tension, where the universe seems to be expanding at two different speeds at the same time, which shouldn't happen. The James Webb Telescope is finding these huge, mature-looking galaxies from the dawn of time that just shouldn't exist yet. And the biggest one of all are two pillars of physics, gravity for the big stuff and quantum mechanics for the small stuff. They just don't talk to each other. These are not small issues. They're giant neon signs screaming that something fundamental is missing from our understanding. So what if the solution isn't adding more complexity, but rethinking the simplest thing we can imagine, the vacuum of space? And that's where this new perspective comes in. It's called dynamic vacuum field theory, or DVFT for short. Okay, so what in the world is DVFT? Well, at its heart, it's a theory that says the vacuum isn't just an empty stage where the drama of the universe unfolds. No, the vacuum is the drama. It's a physical, dynamic field, and its properties, its ripples, its vibrations, its density, that's what creates everything we see and experience. Gravity, particles, you name it. Let's just put this side by side to really see how big of a shift this is. The standard view, right, it sees the vacuum as passive, totally empty space. And to make our math work, we have to invent and bolt on these extra things like dark matter and dark energy. But the DVFT view says, hold on a second. The vacuum is a physical substance, kind of like a cosmic superfluid. It's an active player in the game, and its own properties naturally create the effects we've been calling gravity and cosmic structure. And think about what that means. If this is right, our decades-long, multi-billion-dollar hunt for a dark matter particle might have been a total wild goose chase. To really wrap your head around this, the theory gives us this amazing analogy. Picture the vacuum of space as a vast, incredibly stiff gel that fills everything. The density of that gel in any given spot is what we feel as mass and gravity. And the tiny little shivers and vibrations traveling through that gel, well, that's what we see as quantum particles and all their bizarre behaviors. Okay, so that's the big, mind-bending idea. But how does thinking of the vacuum as a stiff gel actually solve those cosmic puzzles we talked about? Let's dig into the details. This quote right from the source paper really gets to the heart of it. It all comes down to a key property of this vacuum field. It's stiffness. And what that means is that it resists being changed, and it stays synchronized or coherent over absolutely mind-boggling distances. This whole idea is called vacuum coherence. So how does this coherence actually work? Well, think of it like a giant lake freezing over in an instant. First, way back in the early universe, the vacuum settles into its most stable state, and its phase aligns everywhere all at once. The whole surface of the lake just freezes together. Second, because of this incredible stiffness, that alignment holds firm across the entire universe, even connecting regions that, according to the speed of light, should never have been in contact. And here's the kicker, number 3. This built-in long-range order naturally explains why the universe looks so smooth and uniform everywhere we look. It solves the famous horizon problem without needing to invent a whole separate period of cosmic inflation to do it. But here's where it gets really good. This theory's power isn't just for the big cosmic stuff. Let's zoom way, way down into the quantum realm and see how the exact same idea of a dynamic vacuum might crack some of the weirdest puzzles in physics. All right, first up, we've got the neutron lifetime puzzle. This one is a real head-scratcher. Physicists have two different ways of measuring how long a lonely neutron can survive before it decays. The problem? The two methods keep giving two different answers. The first method, it's called the beam experiment, clocks the neutron's lifetime at about 888 seconds. But the second method, the bottle method, gets a totally different result. around 879 seconds. Now that 9-second difference might not sound like much, but in particle physics, it's a canyon. It has been driving physicists crazy for years. So DVFT comes along and offers this wild solution. It suggests that the physical container, the bottle in the experiment, is literally affecting the vacuum field right around it. It kind of squeezes the vacuum, changing its local density. And this tiny little change to the fabric of space itself actually alters the fundamental rules of physics just in that spot, making the neutrons decay about 1% faster, which, it turns out, perfectly explains that missing 9-second gap. And what about this deep question? We know tiny particles can be in two places at once, right? That's superposition. But why can't a cat, or you, or me do that? Standard quantum mechanics never really gives us a clear answer about where the quantum weirdness is supposed to stop and the normal world begins. DFT doesn't just shrug. It makes a specific, testable prediction. It says that an object's mass actually disturbs the vacuum's underlying rhythm. And if the object gets too massive, that disturbance becomes too much for the vacuum stiffness to handle, and poof, the superposition collapses. The theory even calculates the limit, about 100 million atomic mass units. That's a hard number that scientists can actually aim for in future experiments. Okay, so the theory offers these really elegant solutions to some huge problems. But, an idea in physics is only as good as its predictions. It has to match the cold, hard data. So how does DVFT hold up when we compare it to our best observations of the actual universe? This, right here, this is the final exam. It's the cosmic microwave background, the oldest light in the universe, our baby picture of the cosmos, mapped by the Planck satellite. Any theory about the universe, old or new, has to be able to explain this exact pattern, no exceptions. So this is the moment of truth. Can a theory based on a living vacuum actually reproduce this incredibly precise map of where we all came from? And the answer is pretty incredible. Have a look. On the left is the pattern of cosmic fluctuations that pops out of the mathematics of DVFT. And on the right, you have the real data from Planck. I mean, the visual match is just striking. It's not just kind of similar. The peaks, the valleys, the clusters, they're all in the right spots. And let's put some numbers on it. The theory's predictions for that baby picture of the universe, they fit the real data with a mean difference of only about 4.5%. That's really, really close. What about those impossible galaxies? Well, DVFT actually predicts that galaxies should form faster in the early universe, which is exactly what JWST is seeing. And the Hubble tension? The theory's math naturally spits out an expansion rate right in that sweet spot between the two conflicting measurements, potentially resolving the whole debate. So where does all this leave us? This theory seems to be passing some seriously major tests, from the edge of the universe all the way down to the quantum world. So what's the future for this radical idea? I think the most crucial part is this. Dynamic vacuum field theory gives us a single, physical, unified story. It connects the biggest structures in the cosmos to the smallest quantum oddities with one underlying mechanism. It tries to solve these huge puzzles not by adding more weird ingredients to the pot, but by showing us a deeper simplicity we might have overlooked this whole time, a reality that's literally rooted in the properties of space itself. And that really leaves us with one final awe-inspiring thought. As we build ever more powerful telescopes and more sensitive quantum experiments, we are pushing the very boundaries of what we can test. So could it be that these next-generation machines will finally give us the definitive proof that the vast vacuum of space isn't empty at all, but is in fact alive?